we have this idea of rotating about axes, right? And what are the two concepts called? What was the title of, what are the words? The disc and the washer. The disc, we call it the disc because when we revolve around an axis, you just get a solid shape, right? And if I slice it, I get a bunch of discs. What's the washer?
When it's not. You guys take a part facing.
What'd you say? When there's a gap, when you have like one function and another function, and you're rotating both of those, right? So you end up with like kind of a hole drilled out of the object. So it's a washer. Okay, so we're going to use those, but what have we been revolving around lately? The x-axis and the y-axis. We're going to change our line of symmetry in a sense, or our line that we revolve around. Okay? Let's see if you guys can remember this because it's been a whole week. You guys remember the formula for the disk method? Pi integral of?
Oh, bigger one?
Well, but the pi is part of the area, right? It's just the integral of the area function, and because it's a circle, when we revolve, it's the integral of pi r squared, right? Okay. So let's see here. What do I got? Let's try this one. Let y equal e to the x be rotated about the y-axis. See if you guys can come up with an answer here. I'll give you a couple minutes, okay? I'm revolving it. I'm rotating it about the y-axis. What is the volume of the solid that is generated? So graph it. All right. So that's what the graph looks like, right? And we're revolving that region around the y-axis. So the very first thing we have to do is get everything in terms of y. So we're going to say, let's see, x equals what? What's x equal?
Natural log y.
Natural log of y, right? The heart thing, whatever you do, right? You got to rewrite it. So x equals natural log y. The next question you ask yourself, and now honestly I have the answer up there already, but is this a disk or a washer? Is there a hole inside this object as I revolve it or not? It's a solid object, so it's just a disk, right? So how big, we'll do an example in a second. How big is the radius? Well, the radius is changing.
Yeah, it's changing as you go.
The radius is the distance from the center of revolution to what? To the curve, right? So it's whatever this function is, and this is the function. No, it's this because we're looking at it horizontally instead of vertically. So how long is this? Natural log of y. You guys okay with that? Okay, so what's my equation? Pi integral from 1 to e because we're looking at y direction, right? Of natural log of y squared. Y squared? Y squared. Because remember, the general formula for all of this stuff is the integral of the area function. Right? And the area of the circle, as I slice it, is pi r squared. And pi is constant, and the radius, in this case, is the function, so it's natural log of y, and then squared. Because we're gonna revolve it around different lines instead of just axes. When we are revolving about a y or an x-axis, then it's just whatever the function's value is. So we should have gotten 2.257. Most of you didn't do that. All right, are we good with this?
Yeah.
Okay. Washer method. So now this time I'm going to revolve around the x-axis. Maybe I should have done the y-axis just so you could see a little bit more of it, but we will in the future. You got a curve. You got from x equals 1 to x equals e. And then you have natural log. What's natural log look like? Natural log is this, right? Well, what's e to the x look like? Which one's higher? E to the x. You guys should remember this. Natural log of x should look something, well, e to the x looks something like this, right? Where this is 1. Natural log of x, this is 1, and it should look like this. This should be a reflection. If you flip it along the y equals x line, they should be the same. You guys see it? Because natural log and e are inverse functions. Anything that's an inverse can be reflected about y equals x. So that's the general shape of it. And what are we trying to do? We're trying to revolve from 1 to e. So we'll call this e. We're revolving this region. Where's this region?
Can you draw the line?
That's what I'm trying to do. This line, you mean?
Yeah. Wait, but the dot's aren't down.
What?
Well, above E, like there's no dot there. Because it's not bounded. No, draw the dot. We're bad at this.
This is the region we're talking about, right? Okay. Are you guys okay with this? So we're looking for the region from 1 to e that's bounded by natural log of x and e to the x, and we're rotating it about the x-axis, so it's going this way, right? So what's the bottom going to look like? It's going to be this reflection, right? And it'll be kind of like this, right? So yeah, do you see a disc or a washer here? It's a washer because you have a cavity in it, right? So if I'm looking for one piece, I'm looking for something that looks like this, right? One slice. What is the area of that slice, that red slice? Area equals, how would you find the area of that donut? Or that washer? Pi big R squared minus pi little r squared, right? That is just the area, right? So now our formula for volume is what? Take out the pi, because they both have pi in it. The integral from, what's a to b? 1 to e in this case, because we're going from 1 to e, of big R squared minus little r squared dx. Why dx? Because that's how thick the slice is, right? Now, what is big R? The outer function's radius. So the distance from here to the center of rotation is big R. And what's little r?
The space.
It's this guy, right? It's getting messy. So what would we say? Pi times the integral from 1 to e of e to the x squared minus natural log of x squared, right? Dx.
Wait, so can you make that like e to 2x minus 2a?
Well, careful here. You're half right. So e to the x squared can simplify to what? E to the 2x. This, you would be tempted to put the 2 in the front, right? This is equivalent to 2 natural log of x. Because what am I squaring? Just the x. But here, what am I squaring? The whole thing. So you can't move the 2 to the front. Okay. So just leave it, yeah. So that's your answer, whatever that works out to be. There's a better drawing, right? Okay, so. All right, are we comfortable with that? Those two concepts? No? Now? All right. The key that I want to point out, though, is it's all about finding out what the radius is. If you can determine the radius, you've got this. The radius in every concept or every problem I've given you so far has always been the function's value, right? Because we've always revolved around the x-axis or the y-axis, right? But what happens, let me get rid of this and give you another shape. What happens if I take, let's say, this e to the x, and I revolve it around, let's say, -1 instead? Okay. What happened to the radius? It got bigger. You guys see why?
Yeah.
The radius is the distance from the curve to what? The axis, right? Whatever axis we're revolving about. If I'm revolving about the x-axis, this is my radius. But we're not revolving around it anymore. We're revolving about this. So this is my radius, right? So in this case, we would just add 1. Right?
What if it's not a square?
Yeah, well, you still plug into the formula, but the radius is whatever the function is. So in this case, if this is f of x, then the radius is what? F of x plus 1. Okay? So now, yeah, well, what's the formula for that then? Don't just say squared. That would be volume equals pi times the integral from whatever to whatever. Well, let me do this. Of r squared dx, right? So what is r? F of x plus 1 squared dx. Is that okay? All right, let's see what that looks like a little bit more. Okay. All right, so we're going to look at different axes like we just said. And again, if you know the radii, plural for radius? Yes. Okay. Let's take a look at y equals 1/2 x plus 3. What is that? It's a line. So if I revolve it around anything, what am I going to get when I revolve a line? I'm going to get some, not necessarily a cone, it depends. It will be a piece of a cone though, right? Because if the line is this, right, and I cut it here, I'm going to get like the bottom portion of the cone, right? It could be a cone though. So there's the line y equals 1/2 x plus 3. We're revolving it about y equals 1. So where's y equals 1? Right there. Thank you. You're going to go up 1, right? So what happened to the radius? It got smaller by 1. You guys see that? So this is now rotated, and we can see that we're revolving about y equals 1. So the distance from this curve to the red line needs to match the distance from the red line to this curve down below. But this distance from here to the red line is less than the distance from the curve to the axis. Okay? So we would say, and I always do this, I find this helpful. It's not there yet, hold on. What's the radius?
It's big R squared minus 1.
There you go. You wouldn't say big R squared. So notice how I put this in parentheses, or this little bracket here. That represents the radius. And just think about how big this is. It's not just 1/2 x plus 3. 1/2 x plus 3 is the distance from here down to the axis. So we'd have to do what? Minus 1. So then our radius is now 1/2 x plus 2. No. Stare at it for a second. Make sure you get this. The radius is the distance from the curve to the line I'm revolving about, right? So how far is it from the curve down to the x-axis? Down to the x-axis. This is the distance. This is the distance to the x-axis, right? So how far is it from here down to the center of rotation? You got to subtract 1 from that. Does that make sense? Okay, so what would my formula be? Is this disk or washer? There's no hole in it, right? So it's disk. So it's volume equals pi times the integral from 0 to 3, because that's the limits I said. And then r squared, r is 1/2 x plus 2, not 1/2 x plus 3. And then we square it, because r squared. And then that works out to be 73.042. We could have actually figured that out without calculus. Without a calculator either. Watch. Let's verify it. Looking at this line, what is it, up 3? Something like this, and we're revolving it about this. When is this line going to hit the axis of symmetry?
There.
It's going to hit like right here? what is that point? In other words, 1/2 x plus 3 has to equal 1, right? So 1/2 x equals -2. So x equals -4. You guys okay with that? If I go from -4 to 3, what kind of shape am I going to get? I'm going to get a cone, right? So let's revolve this around there. How big is the radius if it's a solid, just a cone? Well, first of all, what's the volume of a cone?
1/3 pi r squared times h.
1/3 pi r squared times h. Okay, so 1/3 of pi times what's radius? What's the radius?
The function minus 1.
Well, it's whatever. This is a static thing. It's not calculus. Just what's the radius? The radius of a cone is whatever the biggest radius is. So how far is it from here up here? That's when x equals 3.
3 halves plus 3.
And then we're going to subtract 1 from that. Okay, so this is 1/2 x plus 3, right?
Yeah, okay.
Okay, so I'm going to plug in 3 to figure out this height. 3 halves plus 3 is 4.5, right? That's the distance from here to here. So how far is it for the actual radius?
3.5.
So the radius is 3.5, right? So 3.5 squared. What's the height?
7.
All right. Now that is the volume of the big cone, right? Now let's find the volume of the little cone.
Why is it a little cone?
Because we're looking for the volume in this region. So I'm going to find the volume of the whole thing, and then minus the volume of this guy, and I'll get the volume of that. Right? That's just a geometric concept, isn't it? Do you not see the cone there? So pi times, now we're going to find the volume of this guy, and we're going to subtract it from the whole thing to figure out what this is. Okay? Wait, what's the radius?
1, 2. Yeah, 1.
This point is what? This one's... No, what's the y-intercept? 3, and this is 1, so it's 2. And then what's the height? 4. So whatever that is. So what are we going to do with these two numbers? So it'll be 1/3 pi times 3.5 squared times 7 minus 1/3 pi times 2 squared, oops, times 4. You guys just get your calculator out and do that real fast. That's just a, I guess that didn't matter, but that's how you would solve this geometrically, right? Because this is it's a line, right? It makes a perfect cone. If it was this, you couldn't do it geometrically. Because you don't know the volume of whatever shape that is. All right, enough of this. Let's see if you guys can actually do one. Hey, give this a shot. And do me a favor and actually try. Don't wait for me to just give you the answer. So this is the piece of tangent that I'm looking at. Tangent would normally look like this, right? And we're going from 0 to 1, so that means we're only looking at this piece. Okay? Now, we're revolving it about what? -2, so we got a line below. So what happened to the radius? Did it get bigger or smaller? So what is the distance from the curve to the x-axis represented by? Tangent of x. What is the distance, what is the radius represented by? Tangent of x plus 2, right? So our formula should have been, what? Well, so our radius is tangent of x plus 2. Notice it's tangent of x plus 2 is the whole radius. We're not squaring tangent of x and then adding 2. We're saying tangent of x plus 2 and then squared. Right? What did you guys get as an answer? 22.054. All right. Are we good then? Hold on, I got two questions.
That's the same question.
Why is it plus 2 and not minus 2? How did the distance get, what happened to the distance from the curve to the radius, or to the center? Did it get bigger or smaller? Bigger. If the line was up here, then it got smaller. We'll talk about that. That gets kind of
Wait,
weird.
so just say like, oh, the function minus whatever like the new thing is, because technically.
Yes.
All right.
Okay, sine of x is this. Right? Victoria? Sine of x is that about, right? And we're going down to 3. So the radius is the distance from here down to there. So this distance here is sine. This distance is 3, so the whole radius is sine of x plus 3. Okay. All right, let's take a look at a washer method on this one. Okay? I got 2 more. Okay. Let the region bounded by x equals 1, x equals e, natural log of x, and e to the x be rotated about y equals negative 1. Okay. Yeah, we already talked about it, right? We talked about all those parameters, except when I'm rotating about the, which axis? No, the whole thing is expanding a little bit.
Wait, where's the x-axis?
The outside is also getting bigger because the outer radius is also getting bigger. Because instead of taking this object and rotating it about here, we're rotating it down here. Right. No, the functions are the same. Yeah, I guess.
First one I was just the
Okay. So that's the original, right? There's e to the x, there's natural log of x. You guys okay with that? What's wrong with it, Joe? What's wrong? Okay. We are rotating about y equals negative 1, so that's down 1. So it's going to look something like this. So now we kind of have... You guys are supposed to get excited about the calculus, not the pictures. It's like reading a book. Does the book have pictures?
looks like a long.
All right. So here's the big question. This is a washer, and you guys can see why? Because there's a hole inside of it, right? How big is the big radius?
The function plus 1.
It's going to be the upper function plus 1, right? And how big is the lower radius? The small.
The function plus
The lower function plus 1.
Oh.
Okay? So we can say
Wait.
the outer radius or the big radius is that distance. What's the upper function? E to the x, so what's my radius? E to the x plus 1. And what's my lower or my inner, my smaller radius, my inner radius? Natural log of x plus 1. And then when we go to plug that in, remember it's the volume of one minus the volume of the other. Actually, take a step back. Whoops.
Oh, that's too far back.
Thank you. Okay. Remember, you can separate this into 2 separate integrals. You could find the volume of the entire thing and then subtract the thing you're removing, right? So what would the volume of the entire thing be? Pi times the integral from 0 to 1, e to the x plus 1 squared dx. That's the volume of the whole thing, right? Now we're going to subtract the volume of the inside thing. So minus pi times the integral from 0 to 1 of natural log of x plus 1 squared. Who said 0 to 1? 1 to e. Somebody told me 0 to 1. All right. But how can I simplify this so it's one nice clean integral?
You just put the Instagram.
Factor out the pi. Since the limits are the same, we can put it together. So it would be e to the x plus 1 squared minus natural log of x plus 1 squared dx. You cannot take out the squares. That's like saying x squared minus y squared, basically. You can't do anything. You could say x minus y, times x plus y. But that's just making it really complicated. Okay. Are you guys okay with seeing this? There's your pi. There's your big R squared. There's your little r squared, right? Yeah. Yeah. All right. Okay. Are we okay with this? It's going to take practice, but you guys got to practice it. You can't go, okay, well, we're almost done. Year's almost over, so I'm not going to do anything and just hope for the best. You will see on the AP exam, I can almost guarantee one of the FRQs, part A will be find the area under the curve. Part B will be what is the volume when you rotate this object about whatever axis. And part C will be what's the volume if I cut it into perpendicular cross sections that are triangles or something like that. We'll get there when we get there. Just, are you okay with this? Okay. All right, I got one I want you to work on all by your lonesome. First quadrant, x squared y equals 2, and rotated about x equals negative 1. So graph it a little bit. Graph the region in the first quadrant. Can you guys, when you have it graphed, can you lightly shade in the region I'm talking about? All right, we're going to have to go over because I don't want to run out of time. Look, listen, you guys are all trying to convert it and then graph. Just graph the dumb thing. X squared is this, right? Y equals 2 is this. We are only talking about the first quadrant. So it's bounded by the curve, it's bounded by this, and it's bounded by the y-axis. So this is the thing that we're revolving. What are we revolving it about? So x equals negative 1 is back here, right? Now hold on. Is this disk or washer? If I'm going to take this and revolve it around there, you see a hole here, don't you?
Why?
Because how far is it from here to here? So that means you're going to have something else coming up like this. Do you see that?
Yeah.
Now, how big is your big radius? Something plus 1. What? It's, you got to get this, you got to convert this, right? This is rad y plus 1. What is the little radius? It's just 1. Okay? We'll finish it up tomorrow. Okay?